Okay, so I would like to take the opportunity to thank the organizers, and I should make sure that I have half an hour, right?
Half an hour.
Plus maybe five more minutes on top. just out of reasons of equity, right?
You get 1 minute more.
Okay. All right. So what I consider is, consider you have a vessel that contains a material that can undergo phase transition. So we would have two phases. So one, and just for simplicity, I draw this phase as round circles. It was just simple to draw it, but you should think of that, of course, it can have any shape you want. So the dark blue would be one phase, omega 1, then the complement is the second phase. So you want to be sure that there is no boundary intersection. You want to be sure that the phases do not touch. There is a sharp interface separating the phases, gamma of t. You will see that, well, that's a convention, so it will have an outer normal pointing from omega 1 into omega 2. Of course, then with any free boundary problem, there is a normal velocity, so the velocity in the direction of the outer normal. Then you will see me using a lot the mean curvature of gamma of t. So that's in this talk the sum of the principal curvatures. And you will see that I'm using a lot this notation, a bracket. And what it does for us is, so if you have a function defined v2 in the wide region and continues up to the boundary, so if you approach it from outside, and you have another part of the function living inside, so you look at the difference or the limit coming from outside minus the contribution coming from inside. And that's just a matter of wording or language. So omega 1 would be the dispersed region, and you will see that it's important for my talk that it can have several components, so one or several components. Now what I will do is I will introduce the system variables, and the system variable will be absolute temperature. Here we go. So the absolute temperature is something that I will insist is continuous on omega, or even in the closure. Therefore, you can take it and then restrict it to the boundary, to the moving boundary, and it is convenient to give it a known name, so the restriction. And you will see a little bit later, once in a while, I will take that as an independent variable, although it's just created as the restriction of the temperature. Now, each phase, or in each phase, so think of water and ice, each will have a free energy, and again distinguished by ice, so free energy for phase 1, free energy for phase 2. So that's something that's a constitutive assumption, so it depends on the material, what it is. And building up on that, once you have a free energy, you can go back and use thermodynamics, so a free energy, and again for me, in this talk, temperature is the independent variable. Thermodynamics, you can go the other way around. You can also take the entropy and express temperature by it. So once you have it, this gives rise to an internal energy. It's a sum, a contribution from the free energy. Another part coming from entropy. You should think with this part, you can do work, and with this part, it's kind of generate, you could think of, it generates heat. So it has entropy, and there are two more quantities that come out from the free energy. One is heat capacity, and the free energy determines entropy, heat capacity, and then latent heat. So in this talk, I would like to make sure that the heat capacities are positive, strictly positive. So it has to do, I want to have a strictly parabolic problem. Then you will see me using that later once or twice. So it's also an assumption, a constitutive assumption, that the material allows for exactly one melting temperature. So you should keep in mind melting temperature would if you have a phase or if you have a boundary that it's exactly straight, then that's the melting temperature. But you will see a little bit later, you can also be in equilibrium, thermodynamic equilibrium, like at negative or positive temperatures. This has to do with curvature that comes in. And just to give you one possibility of a free energy, so you can look at this, And what it does for you, so I just took constant heat capacity, and basically the equation dictates what it looks like, or the other way around. That's something that you would also see in application. So the typical term here, and that would give you an internal energy that then obviously is linear in the temperature. And you will also see I will from now on not always insist on the index I, but keep in mind that all the physical quantities can really be different. Different phases can have different physical quantities. Now the next assumption is, so you have surface tension, and here you have the freedom either to assume that it's constant or you can make it temperature dependent. And I will try to convince you that this has a huge impact what it does for the equation or for the modeling. And also, like if you admit for temperature dependent surface tension and you would be in the framework of fluid dynamics, then that would allow for Marangoni forces. So if I allow the temperature, the surface tension to be temperature dependent, then I have no other choice to also do thermodynamics on the boundary or on the moving surface, on gamma of t. So this would be different if sigma is constant, then I don't care about thermodynamics on the evolving free boundary. But here you have like the companion quantities. So this you would then consider as a free energy, and then you have surface internal energy, you have entropy, and so on and so on. And also surface heat capacity. Again, I would like to be positive. This is something that comes from physical consideration, so it will be decreasing. Of course, only defined temperature is absolute temperature, so we want to stay away from zero. There's a critical temperature. Now, having these quantities, you have two distinct physical functions. Then you have energy and you have entropy. And energy, what is energy? You have in the bulk phase, you look for the bulk internal energy. On the evolving surface, you have this contribution. You go down, you have total entropy, so you have a contribution in the bulk phase, and you have a contribution on the evolving interface. And again, keep in mind, epsilon would have a jump across gamma, so epsilon 1 is not necessarily epsilon 2, the same here. Now, what you would like to have is, of course, a model that is thermodynamically consistent, so it should conserve energy, and entropy should be non-decreasing. So what do you do? Well, you have balance of bulk energy coming in, and right now you're free to do with the heat flux. So that's well, you'll see what we're doing in a second. So you have a heat flux in the bulk, and you have a heat flux on the evolving hypersurface. And this you should read, that's the Lagrange derivative in normal direction. So keep in mind that even though...
Can I ask you a question?
Sure.
So in the balance for the energy, you just disregard any mechanical effects.
Yeah. Yeah. And so it's only heat friction. And keep in mind, so although this looks like something that is stable or stationary, this evolves with time. So you have to be a little bit careful if you define what's a derivative, because you have quantities in general that are only so you really mean derivative in normal direction. So two more constitutive laws. What is heat flux? Well, Fick's law, so proportional to the gradient, and another type of Fick's law on the evolving interface. So taking things together, you have, so you want to insist in conservation of energy, you want to say something about entropy production, and entropy is caused by, if you want, by friction in the bulk phases, and if you want, by friction on the evolving interface, and there is also a possibility for kinetic undercooling. So if you take this principle, conservation of energy, combine it with the entropy production, then you end up with a Gibbs-Thomson law, and that's something that you can derive out of, so we can derive it from these principles, or it has also been derived before by different authors. I will come back a little bit later and show you like another way to read that, the more familiar way that the temperature is proportional to mean curvature, that I will do in a couple of minutes. And I take the liberty either to include kinetic undercooling, so it can be 0, or it can be positive. But it changes the problem. So it's for experts, it's known kinetic undercooling makes the problem, in fact, easier. Now, once you have it, well, then this is what comes out, the conservation, the bulk phase. This is another way to saying that temperature is continuous. This is just a way to introduce language. Then you go on and you have a nonlinear boundary condition, and that you really have to read at the moment as a stationary condition on the evolving boundary. It's of course because curvature is nonlinear, so it has a nonlinear effect here, or a feature. It has a nonlinear effect for the jump in the free energy. Now, this is what comes out on the evolving interface, so read it as a heat equation, if you want, on the evolving interface. So time derivative, and then a divergence, and this is things that, well, I will show you a little bit later what would happen if you take surface tension to be constant, and you will see a more familiar version of the Stefan problem. So what are the variables? Temperature and geometry. And again, it's convenient to introduce this auxiliary variable, but again, it's not a free variable. It's more of a language. Compare this to the Stefan problem where you have constant surface tension, and you will see what's happening is, so this is the Stefan condition that many of you have seen before. Stefan condition, although with inclusion of kinetic undercooling, and this is Gibbs-Thomson just as before. Now, what makes the Stefan problem with surface tension really difficult is the stationary boundary condition, because somehow you're making a statement about temperature equals mean curvature, so it brings in, or proportional, it brings in, this is a difficult condition to handle. It's also because of compatibility conditions, it immediately forces you to have a solution living on a manifold. Now, it's probably instructive to just see, while going back and looking at the principle that there is a melting temperature, you can just do a first approximation. You look at relative temperature and go back to the equation and express everything by means of the relative temperature. And what you get out is something that is probably more familiar, the Stefan problem with surface tension, and here you clearly see that relative temperature is proportional to mean curvature. If you were to set sigma to be 0, then you would be back at the classical Stefan problem with kinetic undercooling, and if you set this coefficient 0, then it's the classical Stefan problem. So there is a huge literature, of course, for the classical Stefan problem, and many of you in the audience have contributed, so I will not write down names, so let's just look at, once you include surface tension, or if you want, mean curvature. So this is like the results dealing with weak solutions. Look how, so global weak solutions, non-uniqueness, these are contributions towards like local solutions, but classical solutions. These are contributions dealing with equilibrium stability and also well-posedness. And this is a contribution looking what happens if you, for instance, send sigma, the surface tension, to 0. So if it comes to the modeling, Gertin has done a tremendous, various papers with modeling aspects. This is an interesting paper, and also like some modeling comes out of our own papers. So what can you expect? And I will show a little bit later, so I guarantee you that I have solutions. So whatever looks formal here can actually, it's rigorous. So the total energy is conserved. You do that. And it's interesting what is going to happen with the Lyapunov function, or with the entropy. You take the derivative that comes out of the equation, and you see that you have the non-negative sign here. So what you see is, so that's entropy production. What causes it? Well, friction, kinetic undercooling. If you're in a situation where no entropy is produced, if you have a 0 here, then what would you conclude? Temperature will be constant, first like constant in the different phases, but because I assume theta, the temperature, to be continuous, then it's one constant. This one doesn't really give you anything because it's in a sense a dummy variable, and this gives you something for the stationary equation. So what comes out is, if you are in equilibrium, you would be at, or if no entropy is produced anymore, you would have constant temperature, and you would know that that for your geometry, that curvature must be constant, comes out of this, and then you immediately conclude if you have compact, embedded hypersurfaces with constant mean curvature, the same, then you know it has to be spheres. So you're back, if you're in the equilibrium situation, then you are, if you have one sphere, well, you're at one sphere, otherwise, however many components you admit, but these are spheres with the same radius, or to say differently, the dispersed phase will consist of finitely many balls. So you would see, well, let's continue. So that's what I convince you, like these are the equilibria. And you also see that you have many equilibria, in fact. So if m is the number of components, then you can look at, so if m happens to be 1, then you have one sphere, one ball. So for the energy doesn't care what you do with a ball, so you have 3 degrees of freedom, and you can take it and make it larger or smaller. And if you have m balls or m spheres, well, then you have m times n degrees of freedom, but you can only change the radius, like they have the same radius. So you're really living on a manifold of equilibrium, and I can prove it is really a manifold. It's not just counting the degrees of freedom, it is a manifold in an infinite dimensional function space. So it's interesting that you can locate where the critical points are, and the way you should think is, so if you ask for equilibrium, you give yourself an energy level, and on this energy level you're asking where are the equilibria. And the answer is, like with a prescribed energy level, you look at the critical points of the entropy. That's where they are. So of interest are critical points which are local maxima, because if you are a local maxima, there is no way anymore that you can, it will not produce any entropy anymore. So that means you're kind of an equilibrium or thermodynamical equilibrium. That's what you expect if you're a local critical point at a local maximum. Can perturb it a little bit, but it will fall back to where it was. So that's true. Well, this is what comes out. You will see so you will only encounter local maxima in the connected case, not otherwise. This is a hint that if you're non-connected, you should not in general not expect stability, but there is a little surprise in there. And it turns out that, so you can also check when you have a local maximum, and this is a condition that comes up, and it's also a condition that comes up for stability considerations. What is the star? Keep in mind that sigma was temperature dependent. You can take the surface tension and evaluate it at the critical temperature or constant, and by notation this gives a star. Same thing for heat capacity, same thing here. Again, that's the equilibrium temperature. That's latent heat at equilibrium. That's the radius of the ball or the sphere, and this just means the surface area. So this is a physical quantity, and you see depends, you can think of many ways to change it and make it smaller of 1 or bigger of 1, although they are connected. Sigma is, so this in fact depends on sigma, but you see that there are ways that you can change the number. Now, since you're looking at this dynamic condition, it turns out that it has, for an analysis, a very surprising or beneficial effect. So you could first look at this equation and assume that you have positive kinetic undercooling. Then the way you would read it is something like, well, normal velocity equals the right-hand side. But this looks somewhat like this equation. If you isolate it, this looks like a mean curvature flow. So embedded in the whole physical system is an equation, this equation, which it's a dynamic equation. It looks like a mean curvature flow. So things seem completely different if you have a zero here. And it appears that you would be stuck with the dynamic condition here, dynamic boundary condition. But there is something that you can do. So this is given. And this is something, you will see that a little bit later, that it's a compatibility condition. I would have to enforce that on the initial data. But you can take that and take a derivative and do some more computations and use up what's in here. And you end up that you can combine these two equations actually into a dynamic equation. And that also looks like a mean curvature flow, although this is non-local here. So this problem, like even in the case that gamma is positive, that gamma is zero, so no kinetic undercooling, you still have a dynamic condition in here. Now, and you can go, yeah. So let me quickly take you through this. So what are the unknowns? What are the system variables? It's temperature, and then if you want shapes, moving hypersurfaces or closed hypersurfaces. So the solution will have, well, it's temperature and it's geometry. So the variable is, so I will insist temperature, I will insist it's continuous, and this notation without writing it up is, and 0 means I would just like to consider one case, gamma equals 0. This means you are collecting H for hypersurfaces, 2 for C2, M for manifold. So this collects all the possible shapes that you have. If you insist on one component of connectedness, well, then you would have all the possibilities that you have, like to bound the domain, like omega 1 inside of omega. If you insist on several connected, then you have more. But this is geometry, and these are really the system variables, temperature and geometry. So you will have to impose, in order to solve the problem, you will have to impose some compatibility conditions. So the temperature from the very beginning, so that's what I will have to impose at the beginning, but then I tell you that I can solve the problem and it will persist. So you cannot be at 0, it's absolute temperature, and you want to insist on this condition. This is the compatibility condition connecting temperature with mean curvature in a slightly different way. And this is a little bit more difficult to understand. So this has to do with the process that I sketched of taking the stationary condition and making it dynamical. So on the way to be successful, there is something that you have to solve. And you see, well, I told you you take derivative, so it's the linearization of the mean curvature. So this is, if you want the linearized mean curvature, second order operator like Laplace-Beltrami plus the total curvature, and this is, you shift it a little bit. So it's, well, you shift it. So you want to insist that this is invertible, and then I tell you I will have, at the beginning on a short time interval, I have a solution under this regularity assumptions, but I can start continuing it. So I can, wherever I end up, I keep regularity, and then I can go on and go on. And this makes sense in this geometry, because it generates, for me, it generates back, again, it generates geometry. That means hypersurfaces. I'm telling you that I can preserve the regularity, so you can continue. You have a semiflow. So the question that you're then asking, so it's a maximal solution, what is it going to do? Well, what would be the obstruction to global existence? Well, things can go wrong with the temperature can blow up, things can go wrong with the geometry. You could run into like that you get close to absolute 0, you could go wrong that you hit the critical temperature. This condition, so this is not a physical condition, this has to do with the method, but this could go wrong. Or what you can have is, you could run into the problem that you have topological changes, could have that the interface touches the outer boundary. It can be that they touch itself. So these are all things that scenarios where classical solutions would break down. However, what I do have is, so I tell you like this is a conditional condition here. So if I know a priori that these quantities are bounded and m is just a generic constant, if I know that I'm staying away from absolute zero, if I know that I'm staying strictly away from critical temperature, if I know that this holds, and this is convenient, this rules out an uniform bulk condition, this rules out any problems with the geometry. So if you have a bulk condition, then it cannot bump into the other boundary, cannot bump into each other, it cannot shrink to a point. So in this case, I'll guarantee you that the solution exists globally, and it will even converge to an equilibrium. So you have to know, again, it's helpful, or it's incredibly helpful to have a Lyapunov function, and you combine it with compactness. And so this cannot be an easy proof here, because you have you have a manifold of equilibria. It's not isolated. So if you think of that the solution, it's easy, well, the usual thing, I mean, it's one thing to say it gets close to the set of equilibria, and it's a different story to say it picks, it chooses, it finds an equilibria, and goes towards it. So a solution would and the equilibria are not really distinguished. I mean, they are, you can take them and move them around, and from an energetic point of view, they look all the same. However, nevertheless, it's true. And the other way around, if in case that you already know that you have global solutions, then this is the easy part, then of course you have that. So when would I know that I have global existence? Let's look at the equilibrium situation. And here it's useful to just introduce a little bit some language. So because of what I mentioned, because it has this feature that you can extract out of what looks like in both cases a stationary boundary condition, you can extract a dynamic condition, you in fact end up seeing a quite nice equation with system variable temperature absolute, and this is already transformed. So the way it goes is take a Hansawa transform, you take a sufficiently smooth reference manifold, express everything, and then you have, so H would be governs the geometry, that's the height function. So this is something coming out of the theory of dynamical systems. What is normally stable? So you want to be sure in a general setting that you have an equilibrium. The set of equilibria really forms at least a C1 manifold. You want to be sure that the tangent space to this manifold, while it exists, it's a C1 manifold, has exactly the same dimension as the kernel of the linearization, so all the eigenvalues that you pick up. You also want to be sure that it's semi-simple. So what I'm telling you here, think of having 1, 0 being an eigenvalue of very high multiplicity, namely all the degrees of freedom that you have, and all the spectrum being on the left-hand side. This is normally stable. If you pick up something on the right-hand side, then you call it normally hyperbolic. It's important, so in contrast to like having an isolated point, you really have to be careful that these things match up in terms of dimension, in terms of geometry. So this is, maybe I will skip that, but what you can then do, these are the equilibria, and you can prove that you have a foliation into like leaves consisting of stable and unstable manifolds. So what will come out is, I have to be a little bit careful. So this is the quantity that you saw before, and that is the quantity that tells you whether or not at a critical point of the entropy functional, whether or not you are at a local maximum. If it's less than 1, you are. So this is a quantity, and that's a different quantity, and you would also see, like formally, this only shows up if let's say this quantity, heat capacity, surface heat capacity, wouldn't be 0. So formally, if you are in the situation where you have constant surface tension, then ignore this, otherwise you would see that this quantity is bigger than this one. Now what you can show is, and that's what thermodynamics really suggests, if you are connected and you have this condition, then it means, well, you're at the critical point of the entropy functional at a given energy level, and you're at the local maximum. So you will expect that this is stable, and yes, it is. And you will also expect that if you move away from connected, that it's unstable. And this is true in case that this quantity is 0, but it might not always be true. So there is another scenario, and it only happens if kinetic undercooling is 0, and the smaller of the two numbers, this one, is bigger than 1, forcing the bigger to be even bigger than 1. So also in this case, you end up having something which is normally stable. So, and otherwise, you can look at all the scenarios, it will be unstable. Now, just, well, and then you prove, so this happens at a linearist level, and then you prove indeed that while it exists globally, you have exponential convergence. If it's normally hyperbolic, then it's unstable. However, you have an alternative. If you get close, if you know that the solution stays close to the set of equilibria, then it will also have to converge. And think of it stays close, then it means it's hitting a leaf which is the stable manifold, and that's where it's going. And so this will be my last slide, and I think I can just beat the 10 past. So if you have constant surface tension, then you're not going, so you're not in the situation that well, let's just say constant surface tension. Then what comes out is, if you have one sphere, then you look at whether or not at this sphere, whether or not you are at a maximum of the entropy functional. If yes, you're stable, otherwise you're not. If you have multiple spheres, again in this case, then they're always unstable. And that's something that people expect. You could say that's something like the onset of Oswald ripening. That is what I think what people would expect from physical principles. So what happens here is, this is something that we don't know physically really what it means. Under these circumstances, you can also be in the situation where multiple spheres are stable. But they would not be now anymore at what is called, so their equilibrium means, I mean, it's stationary, but they would not be at a thermodynamic equilibrium. It's something different going on. And thank you very much for your attention.
Any questions? So, okay. So, can you prescribe a simple set of conditions on the initial data that allow for, I mean, suppose you have an equilibrium and you say my solution is very close to equilibrium in several norms, will it be sufficient to say that the solution converges to
Yeah, so that would be stability, yes. Yeah, that would be stability. But it would be its interest with the multiple components.
Yeah.
So what do you expect? I mean, they will move around. And what people have looked at in a simpler situation is that if you have like the quasi-stationary approximation, if you have two spheres or three, and that's something that people have termed the survival of the fattest. So the biggest one survives, and the small ones go to 0. So and you could expect something like that, but it's difficult to prove.
Is it possible to get a weak formulation so that you can continue the flow even in close-up in classical sense?
I mean, there is the Luckhaus formulation but it's.
Can you do it in this general?
I don't think so. But with the Luckhaus, it's not unique. So as soon as you want to get out geometric behavior, long-time behavior, if you don't have uniqueness, there is like not too much you can compare it. You can jump.
Okay, so there is no way of selecting how to go through one of these singularities.
I wouldn't know how. I hope that there are mathematicians out there who would know how to do it.
More questions? Otherwise, let's thank our speakers in this afternoon.